So this video is a review on techniques of integration that should serve as a preparation or as an extra class for your midterm. I'm going to choose the final exam of May 2015, and I'm going to solve these 7-6 integrals that are part of the first problem. What I suggest you to do is that once I write the integral here, you pause the video, first you try to solve it. If you get the right answer, good for you. If not, then go over and watch the video, and that's how hopefully you will see where your mistake is and you will learn something. Before we continue, I just want to remind you about the techniques of integration that we learned. That's the substitution rule. We learn how to integrate a class of trigonometric functions, and we call that technique trigonometric integration. Then we learned about the trigonometric substitution. We learned how to integrate rational functions by partial fractions. And then we learned the integration by parts, right? So this list of techniques that we learned, you should have the picture of this list in your head. And one way to attack each integral is, if you actually at the beginning don't know what rule, what technique to use, then it's good to go mentally by eliminating the techniques that do not apply to a particular question, and then you will hopefully you will be left with the only one that is applicable to a particular question. Moreover, you should know the few new integrals that we learned this semester, especially 1 over x squared minus a squared, which is 1 over 2a ln of x minus a over x plus a, integral of x squared plus a squared, which is 1 over a arctangent of x over a, integral of 1 over square root of a squared minus x squared dx, which is the arcsine of x over a plus c, integral of 1 over square root of x squared, and here you can write plus or minus a squared dx, which is equal to ln of x plus square root of x squared plus or minus a squared plus c, and finally 1 over x square root of a squared, x squared minus a squared, which is equal to 1 over a arcsecant of x over a plus c. And of course, for these if you take the derivatives on both sides, you can figure out what are going to be the derivatives of these inverse trigonometric functions that you should also be aware of. Okay, so what we spent the first week when we learned trigonometric functions, their graphs, domains, ranges, how to evaluate it, is very important for this test. Okay, so let us start. As I said, we will do the questions from the final in May 2015. Okay, and the first question says, find the integral of x cubed plus 4 over x squared times x plus 2 squared dx. Okay, so because here we're dealing with finding the integral of a rational function, right away what do we have in mind? We have partial fraction. Okay, So first, what do we want to make sure? We want to make sure that we can apply partial fraction to this expression here. And what do I mean by that? I mean that first you have to check whether the order of the polynomial in the numerator is less than the order of the polynomial in the denominator. So the highest exponent in the numerator is 3x cubed, right? The highest exponent in the denominator is x to the power of 4, x squared times x squared, that's x to the power of 4, which means that right away we can move on to partial fractions. Okay, once you have decided that the next step is partial fraction, you have to look at in the denominator and make sure what are you dealing with, what kind of factors you're dealing with in the denominator. So we're going to observe x squared as a linear factor repeated, and x plus 2 is also a linear factor, but it's raised to power 2, so it's multiplied by itself, which means it's repeated. So again, linear repeated. And this will help us do the partial fraction. Okay, so x cubed plus 4 over x squared times x plus 2 squared is equal to, so the first factor is linear. That means above I have to put a constant, a over x, plus now the repeated one, b over x squared, plus the second factor is also linear, so c over x plus 2, plus now finish it, the repeated one, x plus 2 squared. Now the next step is to bring this expression here under common denominator, and as I told you in class, the common denominator will always be this one here. So without thinking what is the common denominator, without making the mistake of multiplying all the factors here, just write this one, x squared times x plus 2 squared. This guarantees, because there is nothing to be cancelled, that this is the common denominator, and then think with what do you have to multiply the numerators by. So it's a over x, and I want to express it as a expression over x squared times x plus 2 squared. That means I have to multiply a by x times x plus 2, plus b is already raised, is divided by x squared, so you just have to multiply it by x plus 2 squared, and obviously here I don't have enough space, so I'll write it here. So I said a times x, x plus 2, plus b times x plus 2 squared, plus c. Okay, so the common denominator is x squared, so I have to multiply it by x squared, and just one factor of x plus 2, plus d is already divided by x plus 2 squared, so the missing factor is x squared. Okay, and once I have brought this expression under common denominator, now I can just concentrate on the numerators. Once the denominators are equal, I can concentrate on the numerators, which will help me evaluate a, b, c, and d in our case, right? So we can here just rewrite the numerators. X cubed plus 4 is equal to ax, x plus 2, plus b, x plus 2 squared, plus c x squared, x plus 2, plus d x squared. Okay? So one way you can do this is expand all of this and then group the terms with respect to the powers of x, and that's a valid way to do it. But if we want to speed up our process a little bit, what we can do is that we can evaluate both polynomials, right, at some particular points. So what are going to be these points? These are going to be points that make certain terms here vanish. Which when will they vanish? When we multiply them by 0. So this one is multiplied by x, and this is multiplied by x. So if I evaluate both sides as 0, I get 0 cubed, which is 0, plus 4 is just 4, is equal to a times 0 is 0. That means b times 0 plus 2 squared, plus c times 0 is 0, plus d times 0 is 0. So there you go. I have the value for b. This is equal to 4b. If 4 is equal to 4b, b is equal to 1. Okay? What value of x would make some other factor 0? Well, that would be x is equal to negative 2. If I evaluate this at x is equal to negative 2, this term, and this term will vanish. So let's see what we will have. Negative 2 cubed plus 4 is equal to a times negative 2 plus 2 is 0. So this is gone. Negative 2 plus 2 is 0. This term is gone. Negative 2 plus 2 is 0. This term is gone. So I just have d times negative 2 squared. So what do we have here? Negative 8 plus 4 is equal to 4d. Or negative 4 is equal to 4d. So from here I have the value for d. Okay? So at this point, we can think of the coefficients of x cubed, okay? Why x cubed? Because it's very easy to check what terms are actually going to be multiplied by x cubed, right? So I have x cubed plus 4 is equal to ax squared plus 2ax plus bx squared plus 4 bx plus 4b plus cx cubed plus 2cx squared plus dx squared, if you expand this part right here. But even without doing that, the coefficients of x cubed are what? On the left hand side I have 1 times x cubed, so that means 1 is equal to, what are the constants multiplying x cubed on this side? Well, that's I think I made a mistake here. Give me a second. This is the mistake here. Let me just figure this out for a second. Sorry, so a over x, so I have to multiply it a times x and times x squared. So for that, I have here x squared. So that's going to be ax cubed plus 2ax squared plus 4ax. Sorry about that. Okay, so the constants multiplying x cubed on the left hand side are a and c. Okay, so I have one equation, right, with two unknowns. So I keep this on the side. And if I look at now, what should we choose? If I look at the coefficients of x squared, I have 1, 2, 3, 4 unknowns. So let's keep that one. What if I look at the coefficients of x? The linear coefficients here it's 0, here it's 1, 2. Okay, and I already know b. So the coefficients of x on the left hand side, I don't have x, that means it's 0 times x is equal to, on the right hand side I have 4a, this term right here, right, plus 4b. But I already know how much b is, right? So 0 is equal to 4a plus 4. And from here, obviously, a is equal to -1. Well, if a is equal to -1, one is equal to -1 plus c, that means that c is equal to 2. And that's how we have found the coefficients of a, b, and c. Please make sure that you correct the mistake that I did here if you were following my notes. When you bring a over x under the denominator x squared times x plus 2 squared, you have to multiply a by one factor of x, so a times x, plus this whole thing, x plus 2 squared. Okay. And once we have a, b, and c, what does that mean? That means that this expression, this rational expression, can be expressed as -1 over x plus 1 over x squared plus 2 over x plus 2 minus 1 over x plus 2 squared. And we're going to use exactly that. So here the integral of x cubed plus 4 over x squared x plus 2 squared dx is equal to the integral of -1. So I'm basically rewriting this expression as this sum of rational expression with the appropriate a, b, c, and d. Okay, and I found them here. That's -1 over x plus 1 over x squared for b plus 2 over x plus 2 minus 1 over x plus 2 squared dx. And this is a very, very simple. All of them are very simple integrals. So this is -ln of absolute value of x minus x to power -1 plus 2 times ln of absolute value of x plus 2 minus -1 times x plus 2 to power -1 plus c. And of course you can rewrite this as -ln of absolute value of x minus 1 over x plus 2 ln of absolute value of x plus 2 plus negative times negative 1 over x plus 2 plus c. The second problem is the integral of ln of x over x to power 3 over 2 dx. Okay, and here you should think about what method is applicable. Obviously it's not trigonometric integral, and it doesn't involve this root of sum or difference, so it is not a trigonometric substitution. Definitely not an integral of a rational function in order to think of partial fractions. So the question is whether this is substitution or integration by parts. So if you're questioning whether this is a substitution, what would the substitution be? The only reasonable idea is to take u is ln of x, but then the derivative doesn't give you x to power 3 over 2, but just 1 over x. Okay? In order to express the rest of the denominator, right, you have to go through the substitution, and that is going to complicate things instead of making it easier. So what if we try integration by parts? So let us rewrite this in slightly more convenient form, and you have to identify this as what is going to be your f and what is going to be your g prime, okay? So f of x is equal to ln of x, and g prime of x is equal to x to power negative 3 over 2. Then find the derivative of f, which is 1 over x, and the integral of g prime, which is g, and that's x to power negative 1/2 over negative 1/2, which is times negative 2. And now let us perform integration by parts, right? So if this is f times g prime, then integration by parts says what? F times g minus the integral of f prime times g dx. So f times g, negative 2 times ln of x times x to power negative 1/2 minus the integral of f prime times g, f prime times g. So f prime is 1 over x times negative 2 x to power negative 1/2 dx. And now this integral, when you're going to write it slightly in a nicer form, you'll see that it's very easy to evaluate. So here I have negative 2 ln of x over square root of x. I'm pulling out this negative 2 outside of the integral. So I have plus 2 times the integral of x to power negative 1 times x to power negative 1/2 dx. This is just x to power negative 3 over 2. And as a matter of fact, we have already evaluated that integral here. So this is negative 2 ln of x over square root of x plus 2 times the integral of x to power negative 3 over 2 dx. The first rule that we learned about integrals in Cal 1. And as I said, we already evaluated that integral right here. So the answer is negative 2 ln of x over square root of x plus 2 times negative 2 times x to power negative 1/2 plus c, or that's negative 2 ln of x over square root of x minus 4 over square root of x, plus c. So one more time, for this integral here, we used integration by parts. Problem 3. Integral of x times secant to power 6x squared dx. Okay, so here obviously I have a product between x and this trigonometric function. But before I continue, it is obvious that I can simplify this expression. Why? Because the derivative of this part here, derivative of x squared, is 2x times dx. So 2x dx is just du. What will that do? Well, it will definitely simplify our life in a sense that if we apply this substitution, which is 1/2, right? So only x dx is 1/2 du. So x dx is 1/2 du. And then I just have secant to the power of 6 of u. Okay, so now we just have to evaluate this trigonometric integral, for which we have a strategy how to evaluate it. Why? Because it's secant to even power. And the strategy says if secant is raised to even power, then save a factor of secant squared. Okay, so this, after applying the next substitution, should become your dw. But before we go there, once you save a factor of secant squared, the rest of the factors of secant, express them through the formula 1 plus tangent squared is secant squared. Well, in order to get to secant squared here, secant to the power of 4 is secant squared of u, the whole thing squared, and only secant squared is 1 plus tangent squared of u squared times secant squared of u du. Now you can apply the second substitution, that's tangent of u, let's say, is equal to w, and here, as we were expecting, secant squared of u du is just dw. So our integral, or this whole integrand, sorry, becomes what? Becomes just integral of a polynomial, right? So tangent of u is w, so I have 1 plus w squared dw, and this is very simple. Expand this 1 plus 2 times w squared plus w to the power of 4 dw, and as I said, we have done these types of integrals in Cal 1, so that's w plus 2 over 3 w cubed plus 1 over 5 w to the power of 5. And now be careful, the only trick here is that you have to bring this expression in terms of x, okay? So don't forget that you have to bring it 2 substitutions back. So first we're bringing it back in terms of u. What is w? W is tangent of u, so and then substitute u in terms of x, right? So this is going to be 1/2 tangent of x squared plus 2 over 3 tangent, here I also made a mistake, sorry. So integral of w squared is w cubed, sorry. So tangent cubed of x squared plus 1 over 5 tangent to power 5 of x squared. Of course, don't forget this constant here. So this problem, in order to solve this problem, we first had to use substitution. X squared is equal to u. That brought us to this trigonometric integral, for which we have a particular method how to solve it. We saved a factor of secant squared. What was left of it was expressed through the formula 1 plus tangent squared. Then we applied another substitution, tangent of u is w, which brought us just to the integral of a polynomial, which, as I said, was done in Cal 1. Next is problem 4. So this is the integral of 1 over 4x squared plus 1 to the power of 5 over 2. Okay, so if you have, let's say, some w to the power of 5 over 2, this is what? This is w, square root of w to the power of 5, which is w squared, square root of w, right? So basically, this expression involves this square root of 4x squared plus 1, basically involves the expression of a square root of sum of squares, okay? And this is being solved through a trigonometric substitution, right, involving tangent, okay? So one way how to do this is that you can factor out 4 if you want to, or simply you can recognize what needs to be cancelled with 4 in order here to have tangent squared plus 1. So if you follow that logic, x is equal to 1/2 tangent of theta. Find the derivative in order to find dx. So dx is equal to 1/2 secant squared theta d theta. Okay. From here, let us figure out what the triangle is, right? So tangent of theta is equal to 2x. Theta, we know that tangent is the opposite, 2x, and you can observe this as 2x over 1. So that means the adjacent is 1, and the hypotenuse is going to be the square root of the sum of squares, 4x squared plus 1. As I said many times, the third side in your triangle actually has to be to give you the root that you are trying to eliminate here. Okay, from the triangle right away, you can actually see what the square root is equal to, right? Because if you have secant of theta, secant theta is what? Hypotenuse over adjacent. Right away, that's 4x squared plus 1. And you have that expression. How much is that root? Or if not, you can simply write it right here. 4x squared plus 1 is equal to, now apply the substitution, 4 times 1/2 tangent of theta. That whole thing is your x plus 1. That's 4 times 1 over 4 tangent squared theta plus 1. These cancel. Tangent squared plus 1 is secant squared of theta. So there you go. I think I have a mistake here. Sorry, yes, it's correct, because if you square both sides here, you're going to have that secant squared is equal to 4x squared plus 1. Exactly what I needed. Okay? So let us now apply the substitution. What do we have? First of all, this expression to the power of 5 over 2 ends up being, w to the power of 5 over 2 is w squared times square root of w. So this can be written as dx over the expression to the power of 5 over 2 is 4x squared plus 1 squared times the square root of 4x squared plus 1, which is equal to, how much is dx when applying the substitution? That's 1/2 secant squared theta d theta over 4x squared plus 1 is secant squared, and then the whole thing squared, times the square root of 4x squared plus 1 is just secant theta. So this is equal to 1/2 integral of secant squared theta d theta over secant to the power of 5 theta. And now simplify this expression. That's 1/2 integral of d theta over secant cubed theta. Well, hopefully everybody knows that secant of theta is just the reciprocal of cosine, right? Which means that the reciprocal of cosine is, 1 over secant is just cosine. So this can be written as 1/2 times cosine cubed theta d theta. And now again, if we have sine or cosine to power or raised to odd power, we have a whole procedure how to deal with it. So it says save one factor of cosine of theta, then express the rest of it through the basic trigonometric identity. That's 1 minus sine squared theta here I use the substitution sine theta is equal to u. So cosine theta d theta is equal to du. That brings us to 1/2 integral of 1 minus u squared du, which is 1/2 times, I'm integrating with respect to u, so that's u minus 1/3 u cubed. And now u stands for what? U is just sine theta minus 1/3 sine cube theta. And finally, from the triangle right here, we can read what sine of theta is. So sine of theta is equal to the opposite 2x over the hypotenuse, right? Square root of 4x squared plus 1. Okay, so we substitute this back in here. So that's 1/2 times sine of theta is 2x over square root of 4x squared plus 1 minus 1/3 times this whole thing raised to power 3, that's 8x cubed over 4x squared plus 1 to power 3 over 2. Okay, the next problem is 5, the integral from 0 to 1, x times arctangent of x dx. Here, obviously, the only choice that we have is the integration by parts, right? No substitution will bring us from arctangent to x, and this doesn't coincide neither with the trigonometric substitution, trigonometric integral, nor partial fraction. So we have to identify what our f and what our g prime is going to be. Okay, so we definitely don't want to find the integral of arctangent, so we're trying f of x is equal to arctangent of x, and g prime is equal to x. Then f prime is going to be 1 over 1 plus x squared. You can see how many times we just used the inverse trigonometric functions, and then g of x is the integral of g prime, which is x squared over 2. Okay, so if this is the product of g prime times f, after using integration by parts, this is equal to f times g minus the integral of f prime times g dx. Okay, so f times g, that's arctangent, times x squared over 2, and of course in the next line I'm going to rewrite this in a more convenient way, minus the integral of f prime, which is 1 over 1 plus x squared times g, x squared over 2 dx. Now the only thing here we have to be careful about is what? That we're dealing with definite interval. Okay, so right away I will evaluate this from 0 to 1, and I'm gonna keep this from 0 to 1. Okay, so let us just rewrite this line in a slightly better way. So that's 1/2 x squared times arctangent of x evaluated from 0 to 1 minus 1/2 times the integral of x squared over 1 plus x squared dx evaluated from 0 to 1. Right away here I evaluate this antiderivative, that's 1/2 times 1 squared times arctangent of 1 minus, when you plug here 0, 0 times either this factor or this factor, doesn't matter, both of them are 0, minus 1/2, and here what do I have? Integral of a rational expression, okay? And as we started with this first problem, the moment you have a rational expression, the first thing that you do is check whether the numerator and the denominator are of the same order, and actually they are, right? So you could proceed by long division if you want, which is overcomplication in this particular case. I have to multiply x squared by 1, x squared plus 1. Now you subtract this, and then you just get -1 as a remainder. Or we have done many times these types of integrals. In order to cancel x squared with x squared plus 1, I will add 1, and then I will subtract 1 here. So of course I'm going to skip some complicated procedure like long division in our case, okay? So what do we have here? 1/2, 1 squared is 1, arctangent of 1 is pi over 4. I hope that you already know this. Minus 1/2, and of course I'm going to split this with integral of x squared plus 1 over x squared plus 1 dx minus the integral of 1 over x squared plus 1 dx. Please pay attention to the brackets, okay? Both of them evaluated from 0 to 1. So what do we have here? This is pi over 8 minus 1/2 the integral of dx from 0 to 1, that's just 1, minus this integral here, I hope you know it already, that's arctangent of x from 0 to 1, and that's pi over 8 minus 1/2. So this is the integral. The integral of 1 is just x, evaluated from 0 to 1, minus arctangent of 1 minus arctangent of 0. That's pi over 8 minus 1/2, 1 minus 0, minus this part is 0, this part is pi over 4, and we have pi over 8 minus 1/2 plus 1/2 times pi over 4 is pi over 8. Well, pi over 8 plus pi over 8 is pi over 4 minus 1/2. And this is a typical question of a definite integral for which we had to use the technique integration by parts. And the last integral that we'll do here is the integral from 0 to pi over 3 of secant of x times ln of secant x plus tangent of x dx. Now this might be slightly misleading in terms of this might be misleading because you have a product between two functions, and that might be you might be thinking of integration by parts. But even if you do that, what would be your f? You definitely don't want to take integral of this question, of this part, so you would say this is f and this is g prime, right? And if you do that, if you say f is equal to ln of secant of x plus tangent of x, then f prime is equal to So derivative of ln of u is 1 over u, so that's secant of x plus tangent of x times u prime. And the derivative by the chain rule, derivative of secant is secant times tangent, and derivative of tangent is secant squared. And now if you want to simplify this, right, f prime would be secant x times tangent x plus secant x over the same expression here, tangent x plus secant x. But now these two terms can be cancelled, and what do we get? We get that the derivative of this expression is just secant of x. So instead of applying integration by parts, it would be much easier to treat this as a substitution, because if you take u to be this part of the integrand, then du gives you the whole integral here. So this is just the integral of ln of secant x plus tangent x is just u. And then secant x dx is just du. The only thing is that this is a definite integral, so the limit of integration will change according to the substitution. So here, when x is equal to 0, u is equal to ln of secant of 0 plus tangent of 0. Now secant of 0 is 1, tangent of 0 is 0, so you have ln of 1, but the ln of 1 is 0. So the lower limit stays 0, right? And when x is equal to pi over 3, u is equal to ln of secant of pi over 3 plus tangent of pi over 3, and now we just evaluate how much is this. This is ln. Secant of pi over 3 is 2, plus tangent of pi over 3 is square root of 3 over 2 over a half, just square root of 3. So the lower limit becomes, the upper limit becomes ln of 2 plus square root of 3. And now this integral is extremely simple to evaluate. That's 1/2 times u squared evaluated from 0 to ln of 2 plus square root of 3. That's 1/2 times ln squared of 2 plus square root of 3. Right? If we use substitution for a definite integral, we don't have to bring the antiderivative in terms of x, but what we have to do is change the limit of integration according to the substitution, and then just plug it here and evaluate it. And that's it. This is the whole question. And the last thing that we're going to do is that we will evaluate this integral here. X minus 2 over x squared minus 2x plus 5 dx. Okay. So again, I have an integral of a rational function. The numerator is less than, the order of the numerator is less than the order of the denominator. So there is no need for the partial fraction. And then there is no need for a long division, and now you're thinking whether partial fraction is applicable. The problem is that the denominator cannot be factored. You cannot find x for which the denominator is going to be 0. In this case, right away, what can we do? We should expect that sooner or later we'll have to complete the square. So let's complete the square here. X squared minus 2x plus 5 is equal to x squared minus 2x. Now you have to add and subtract a constant squared. How much is that constant? Just take the constant multiplying x divided by 2, you get 1, so plus 1 squared minus 1 squared plus 5. The first three terms complete the square, plus 4. So this is the integral of 3x minus 2 over x minus 1 squared plus 4. And here even we can anticipate that we'll deal with this integral of a constant over a linear expression in terms of x squared plus a constant squared, which inevitably will end up with arctangent. But here is going to be slightly more difficult, okay? So the first thing that we can do is split this integral. This is going to be 3 times the integral of x over x minus 1 squared plus 4 dx minus 2 times the integral of 1 over x minus 1 squared plus 2 squared, right, which is 4 dx. And this antiderivative I already know how much it is. Okay, that's going to be 1 over 2 arctangent of x minus 1 over 2. But we keep it like this, or we can actually evaluate it here, it's not a problem. For this integral, I have to apply the substitution x minus 1 squared plus 4 is equal to u. What are we going to get is that 2 times x minus 1 dx is equal to du, right? The derivative of 4 is 0. From here, x minus 1 dx is 1/2 du. So you can see I don't have x minus 1 here. I cannot expand this. I cannot drop the parentheses here. So I need to create that x minus 1 here. How am I going to do that? Well, I'm just going to subtract 1, and that's not equal to this, right? So if I subtract 1, I have to add 1. And now basically I haven't changed anything. Minus 2 times, we said that this antiderivative is 1 over 2 arctangent of x minus 1 over 2. Okay? Now I have obtained this x minus 1, so I will group these two terms, and again I will split this integral. So that's 3 times the integral of x minus 1 over x minus 1 squared plus 4 dx plus the integral of 1 over x minus 1 squared plus 4 dx. But be careful, this 3 multiplies the sum of these two integrals, right? So keep the parentheses. Minus arctangent of x minus 1 over 2. Okay? Now for the first integral, I just apply the substitution. So this leads me to integral of the denominator is u, so 1 over u. Why 1? Because x minus 1 dx is 1/2 du plus this antiderivative I have already evaluated once. That's 1/2 arctangent of x minus 1 over 2. And now this is equal to 3 times 1/2 ln of absolute value of u plus 1/2 arctangent of x minus 1 over 2 minus arctangent of x minus 1 over 2. That's 3 over 2. Now I distribute this 3. Basically, I drop the parentheses, right? And I multiply this expression by 3. 3 over 2 ln of what is u? Is this whole expression, right? X minus 1 plus 4 plus 3 over 2, 3 times 1 half, 3 over 2, arctangent of x minus 1 over 2 minus arctangent of x minus 1 over 2 plus c. Now I can add these two terms. 3 over 2 ln of x minus 1 squared plus 4 plus 3 over 2 minus 1 is positive half arctangent of x minus 1 over 2 plus c.